time zone. This is on a short notice. I sort of adapted my talk from a presentation given to Singapore's Urban Renewal Authority. And then by then, I think my purpose was trying to introduce a bit of practice and research related to urban microclimate in Hong Kong, which is quintessentially a high-density cities. I have more slides than I'm able to share, so I think I will pick a few and then just go through them, and hopefully we reserve some time for Q&A towards the end. Okay, so oh, I think there's a button I need to press. Okay. There's no need for me to stretch the importance of the urban heat issue, and that's driving sort of the headline news to public health crisis, and it shaped many of the research priorities. Myself and many other distinguished scholars with me in this forum. And I'm going to sort of structure the talk briefly in these four categories. I'm going to talk about research a little bit, sort of centered around this humid subtropical climate in Hong Kong. I'm going to talk about the driving forces, and probably more interestingly, the lessons from a decade of policies, guidelines, top-down government interventions, and what we can learn from it. Then I'm going to introduce sort of the two dichotomy of policy-driven versus the data-driven design. I think my core message for this evening is that we're shifting from, let's say, a policy-driven approach towards more of the data-driven approach. I hope that will really strike in tone with Professor Yao Jiawei's overarching theme of the architectural intelligence. Otherwise, I have to make sure that I myself sounds intelligent to be able to invite you back to speak in this forum. Of course, this is some overarching theories I think we all share with all the researchers from urban climate, originally from the UK, Canadian, Australian scholars, and then I think Hong Kong scholars poured a lot of energy studying into the phenomenon. I think Professor He Baojie is going to talk a lot about it, so I'm just quickly going to skip. What I found interesting, for instance, is the distribution of research literature across scales. I was able to find a lot of studies published in urban climate, epidemiology, really the large scale, using, let's say, Landsat data set, looking into the land surface temperature variation. And then we have a bunch of studies represented really by scholars such as John, and then your experts in CFD, simulation, building energy, indoor air, etc. I think what we're lacking a little bit is perhaps what I've been doing, teaching in the field of urban design, that boils down to the street blocks, and that's neither considered an indoor or building problem, nor that's considered an urban original problem. So I was just using an example of how do we look into the literature and breaking them down by scale. So I started to sort of conceive studies to develop tools, and then that could assist policies or planning or interventions exactly at the scale of street blocks. So here's actually a recently published study in the UK that we're looking into 3 Welsh cities and looking into their urban heat sort of potentials during future heat waves. And these are sort of frequently catching headlines in the UK, where the population usually is not very adapted to extreme heat wave. I think unlike perhaps people in Hong Kong or Shanghai or elsewhere in the tropics, that we're more or less getting used to it. So we built we call it the thermal digital twin of the center of Cardiff. We built this 1 kilometer sort of a digital sort of properties reflecting the 3D geometries, albedos, surfaces, all sorts of input. And then the outputs are so the hourly, so the human equivalent temperature. We use UTCI, but we can also use PET or SET or many of others thermal meteorological indicators of your familiarity. So you're looking into this distribution of heat waves on a typical or very, very hot day. And you're going to sort of be able to force the model into the future from the past to current to near and distant future, following the IPCC scenarios using the future weather generator of various models that provided as the infrastructure. And that also give us sort of inspiration of where are these locations are consistently hot. And these locations really are at 3 meter or 5 meter scale, and looking at what we call the street block scale. So for instance, the Butte Park at the center of Cardiff, whereas you have find generous tree canopies can deliver a lot of cooling. The medieval urban fabric in the center of Cardiff that also provides some lessons. We're looking into this sort of east north-south oriented streets, such as St. Mary Street. It's very wide, and it's usually actually exposed to the solar radiation in the middle of the day when the temperature is probably the hottest, and versus those sort of east-west facing narrow alleys shaded by the buildings, and of course allowing the prevailing wind from the west to sweeping through, reducing pedestrian heat stress. So this actually, the simulation model be able to show the differences. Then we also looking into the traditional typologies such as arcade. As one example, the Royal Arcade, perhaps as future shelters for residents if you don't have air conditioning at home, which is actually very uncommon in the UK or elsewhere in Europe. And then people perhaps can take refuge during very hot days, perhaps in shopping malls, perhaps in arcade, or these can be so they serve as contingency venues. Our research does not stop in the UK, of course. We study thoroughly what is really going on in Hong Kong. Is probably one of the experiments of high density. We're looking into the contribution of warming at the street scale. And surprisingly, we find that solar radiation actually contributes relatively a small amount, because the shading from high-rise buildings in dense urban core, that's kind of reflected a lot of solar radiation away from the rooftop, for instance. The majority actually of the heat are coming from building HVAC systems and also from traffic exhaust. So these are waste heat from internal combustion engine that are discharged in the urban canyons that cannot dissipate rapidly because of the stagnant airflow. And we also maximize the greenery scenarios. So you can see the green shape underneath. This is actually a hypothetical scenario that we really maximize the tree coverage on Hong Kong street, and then probably maximize about 1/3 to 40% of the surfaces, but then still cannot match the intensity of the heat that contribute from anthropogenic sources. So that's sort of an important lesson, I think, for us to consider when cooling a high density city such as Hong Kong. Trees are perhaps can do only so much. We're not saying it's not useful, but we should also consider other scenarios such as so the evaporative cooling, such as mechanical ventilation, or perhaps radiative cooling, or many other important strategies. And combining these together would be able to achieve sort of a desirable cooling effect in Hong Kong. And then we also looking into how would the heat wave affect people's behavior. I think this is sort of a relatively lighter topic. We're not talking about life and death or people getting sick, but we really want to look into how would heat wave affect people's willingness to use open spaces and outdoors. Because we're urban planners, we're architects, we're really looking into the health benefits of open spaces. If really people are spending time retreating indoors in the air-conditioned apartments, playing iPads or watching TV all the time, and that is also sort of a health hazard. It's not acute health risk, but at least it's something that happened at scale. So we actually took a bit of an unconventional approach. We use social media as a proxy to look into outdoors activities. And in order to do that, we have to geocode them. At the same time, we want to find out how good are these social media data are, how useful are they? Because often you hear the critique of the social media data or many of the big data studies that you have garbage in or garbage out. There's lots of uncertainties and errors, and usually the findings are not very reliable. So actually, we did carefully check the results with small data. So there's actually comparing big data and small data gathered from field measurement, from surveys, from observations that we're really familiar with in the past in the literature. So it's a brief finding. If you actually put sort of big data and small data side by side, if you're looking into sort of the average head count, let's say in Sun Yat-sen Park, which is a large urban park in Hong Kong, you find that's the graph on the left. You would see the slope that's with the 95 confidence interval suggesting perhaps a 1 degree increase in equivalent temperature, you expect a 4% drop in park attendance. Yeah, and this is actually a stark message for Hong Kong that if urban sort of climate change is working against us, and we expect to see a further reduction of outdoor activities in Hong Kong. Okay, that's really a burden for healthcare system. Think about the chronic disease. Think about all the other non-communicable diseases that are already sort of threatening us. And then on the right-hand side, you're looking into the slope of the Twitter-based count. You still see a significant drop, although at slower pace. It's basically 1% drop in Twitter activities geocoded inside parks with 1 degree increase in equivalent temperature. Again, actually measured for the outdoor environment. So this actually conveys unmistaken message that heat, so the urban heat or surges in heat wave is going to affect negatively on outdoor activity, even for a population well adapted to hot climates such as Hong Kong. So definitely there's an urgency for us to do something. And of course, we see the slope differ, and that actually gives a very important warning for us to be very careful in treating social media activities, because usually people exaggerate. People talk about lots of things and lots of mistakes that we encounter in those big data sets. So here an example we discovered. We're looking into the density of where people are. Let's say in the same park. On the left-hand side, you have the small data, the observation. This is actually achieved by recording the head count by research assistants on an hourly basis. And then to the right-hand side, you have this geocoded tweet density. And that's actually really acquired through so the server and data analytics, actually much cheaper. But we see so there's matches and mismatches. I think overall there's good agreement. But we also found there's actually is a dark slot on the right-hand side. And that is about 150 indoor tweets were mistakenly labeled as outdoor tweets in the park. And presumably actually drill into it because these tweets are people hooked up with the Wi-Fi from the swimming hall. And consequently, actually, they were mistaken, sort of labeled as outdoor tweets. So this is also sort of a message for us to take seriously that on large scale, if we don't do data cleaning, we don't sort of check the big data carefully, we may mislead findings. So this is sort of a bit of a reflection on the wave of big data studies we've been seeing in some domains, including our own. I'm probably going to accelerate a little bit. I think I used more than half of my time. Now, this is more or less a structure of government approaches. What can we do to reduce urban heat or enhance urban microclimate in Hong Kong? And there's lots of top-down strategies, but in my opinion, or policy-driven design. But there's less of this bottom-up innovation. There's, I think, not. Well, we have to transition towards sort of data-driven design. We have to sort of drift away from sort of the decade-old business as usual. And business as usual, this is something actually we show you as an example, is that perhaps we use policies or guidelines as the instrument to shape sort of a design or development project. You can use guesswork, or you can use advanced tools such as Hong Kong's Air Ventilation Assessment, AVA, conceived after SARS. And there's incentive schemes. You provide GFA bonus. If you're real estate developers, you receive 10% additional floor areas as profit if you comply with ABC, all those setbacks or coverage or separation rules. And these are also voluntary guidebooks issued by the industry or by government institutions or semi-public, semi-private bodies that actually tells or guide professionals what to do. But these are not mandatory, these are voluntary, so it doesn't have teeth, and then it doesn't have requirement for compliance. Here are the examples in Hong Kong, what entire sort of big new towns and TKO, they're shaped using air ventilation assessment. They use CFD tools in large scale and outdoor settings with some results. I think, of course, there's a lot of criticism towards this approach for reasons I won't be able to delve into very deeply. But the data-driven design will be able to sort of differ essentially from what we are sort of the model before, that we use simulation tools to test various scenarios, and that be able to sort of inform a better sort of result. So this is a build project, award-winning public housing project in Hong Kong that sort of uses such tool to sort of design open spaces that with plenty of shading and pleasant breeze that really kind of create a vibrant, well-used and loved open space that the entire community would gather around. And then we did our measurement and we did our field simulation, and we can prove that because of such sort of intelligent design, allow me to phrase that way, that we can achieve quite a lot in a of redeveloping a 7-hectare sort of a very dense urban neighborhood to begin with. And then this is the business as usual, which most of the Hong Kong developers would proceed if they acquire land from the government. They would double the density or triple the density. But our simulation model would review their intense urban heat island challenges. And then we sort of work with the design team that our model can run quickly, suggesting there's improvements if, let's say, you enhance the breezeway, or where you sort of tweak the building massing, but also making sure that everything comply with the building code and fire code, zoning, and then the square footage is exactly what the developer would like to, so they don't lose money because of this. And then we can also play with building height, again, so within the envelope of the building regulations there. And ultimately we'll be able to sort of deliver a final design that's a 1 degree reduction over the entire hot season on average, and then also double the amount of wind speed on the pedestrians level, and that's not going to sort of cost sort of energy, because this is all realized through passive design. And so this is sort of a chosen design strategy that's been constructed right now. And then sort of we add in a bit of a flavor of what can generative design and optimization, I think, I step into Professor Yao Jiawei's and many of other scholars' research domain. I think that can give us advantage. So the designers, we don't have to guess, and we can actually use computers to tell us in intelligent way what would the favorable design solution look like. So we again use this Sun Yat-sen Park, this sort of a urban park that's about I think 150 or 170 meters sort of as a square, and then it has 55 large trees. These are generous banyan trees, but the practical problem comes in if that if you're going to reshuffle those trees, where would you plant them in order to cool the park in a more favorable condition? Because the trees are limited, the number, you're limited by the budget to maintain, to trim, to fertilize, for irrigation. But I think there's sort of a smart way to find out where would you optimize the amount of cooling given all the design constraints. So we built a tree model, we let it run, and then the trees can sort of generate automatically, but we use a generic algorithm, so that be able to sort of automatically select the favorite, mimicking sort of natural selection. The genes would pass on to the future generation for performing favorably. And eventually, I think to our surprise, we find that the trees are start to cluster together to the downwind side, and we'll be able to find that the canopies are touching each other, and that can sort of reduce both the average equivalent temperature throughout the site in the park. Also can achieve the lowest, the coolest spot. So the use various performance criteria. We actually end up with very similar layout of trees. And I think this actually, we're looking in our eyes, I think none of the landscape architects are thinking of that way when we're conceiving the design like that. And later on, it was so we realized that the tree canopies can also stagnate a wind, because the nature of the simulation built into it's not MVMAT, it's something actually we wrote from scratches. The trees can shade, the trees can sort of evaporates, evapotranspiration can cool the ambient air. It can also reduce the airflow around it because of the porous nature of the canopy. So that's sort of one of the interesting findings. We recently published this in Urban Forest and Urban Greening, and we showed it to many landscape architects. We generate quite a bit of an interest out there. And then model can not only sort of tell us where to reshuffle the tree because it's impractical, where can also tell us where would you add new trees. The new trees are, according to government policy, we have to add a third more trees to the urban neighborhoods. And this actually is a useful tool to tell us if you add it to the advantageous location, you have 3 times as much cooling as if you add it to the least effective layout. Actually, it shows there's quite a bit of a difference in where would you put them. I think lastly, I think my time is running short, running out. I want to show you one example if we use machine learning to accelerate these processes. So this is probably quite straightforward. Instead of using physics model, we would train a neural network model to accelerate the workflow. And then that would be sort of a similar situation to test it in a slightly more complex condition. So we use a piece of Shenzhen, which is just right next to Hong Kong. We have this stringent solar radiation, solar axis law in mainland China. And the building have to look identical because the the developers want to save design fees. But the only variation you have is the location of these buildings and height of them and the building setback within their own property or red line. So here you go. We have this sort of blue line with machine learning accelerated optimization. And we also have a red line where it's sort of a traditional physics-based optimization. And you would see actually the differences are quite a lot. And both of them actually beat the best human design options, suggesting that I think machines did outperform human designers in certain domain, but not all of this. And that's sort of one of these interesting findings. So I need to wrap up. I think what I really want to share, convey the key message that we're encountering challenge that are really site-specific, and we need also site-specific design solutions. But usually that's the weakness of the top-down government policies. Usually you will focus on an entire city or large region with generalizability in mind, but not specific enough. So this mismatch would require new thinking, that we would prioritize the bottom-up innovation, which I frame it as the data-driven design because it's really driven by simulation, optimization, and then later on machine learning tools that are more useful, more nimble, and I think more informative, so that can empower our profession to deliver better design. Thank you very much. I think I will stop here.
Thank you very much, Professor Huang. Actually, I have learned a lot, especially for your newest research papers. Yeah, actually, I need to invite you maybe each half year because you published many papers so in these years. So maybe we can ask for any questions after three presentations. So let's move to our next presenter, John. Yeah. Hi, John. Yeah. So, yeah, welcome, John. And he's from University of Nottingham in the UK. And his talk aims to present a comprehensive overview of the current challenges, novel methodologies, and future directions in the application of AI within architectural design and building operations. Actually, he thinks we can explore case studies and theoretical frameworks that illustrate the application of AI and setting the stage for more sustainable, efficient, and occupant-friendly architectural solutions. Yeah, it's your time, John.
Thank you. Good evening, everyone. First of all, thanks to Professor Yao for inviting me to give a presentation about our research, and also to his team, and also to everyone who's listening today. My topic is a little bit different from, I think, from the presentation today. It's more about indoor environment, but I think I can introduce some of the like AI applications that we're using in the built environment. So the title of my topic is Deep Vision for Enhancing the Sustainability and Energy Efficiency in Buildings. So deep vision means computer vision plus deep learning. Just a little bit about myself. I'm John Colty. I'm from the University of Nottingham in the Department of Architecture and Built Environment. I joined Nottingham in 2017, and previous to that, I was in Leeds and Sheffield. A lot of my research focus before is about using CFD modeling, experimental testing to design low energy cooling systems for buildings. Today, I'm more focused on the application of AI in buildings, energy systems or technologies in buildings, and the application of sustainable and resilient architectural designs to enhance the performance of buildings. I've been fortunate to work with a lot of talented researchers, and they're working on very interesting projects. But unfortunately, I won't be able to talk about all of them today. I'll be focusing mostly on the AI side, specifically on the computer vision applications. We are also very focused on, we try to translate our research into practical applications. So a lot of the technologies or the approaches that we develop in the team, we try to commercialize this or translate this into practical applications. So we have Passiback, which is a company that we've set up so that we can be able to do this. So we've just recently launched our product about these low energy systems. And we also have different types of experiment tests and modeling systems. So if you're interested, I've set up the link, or you can email us later. So today I'm going to talk about the vision-based and deep learning, how we can apply this in buildings. Specifically, how do we use this to aid the control of buildings? And then I'll be providing some examples on how we can apply this in buildings, such as in terms of occupancy detection, equipment use detection, and also the window operation detection. I think my connection is a bit lagging. I'm not sure if you can hear me properly.
Very clear, no problem here.
Okay. All right, thank you. So how can deep learning and computer vision improve the performance of buildings? So first of all, how did I start working on this? So it's one of this experience that I have in teaching in a class in our university. And if you can imagine this classroom, large classroom with a lot of computers, about 100 people or 100 computers. And one day I have this class, and we have about 10 people in this classroom. And the problem is, for some reason, we've been allocated this room, which is for 100 occupancy, and our class is only 10. It's a master's class. There's only 10 people in that room. At some point in this class, we started feeling cold. We started wearing some jackets. It's quite well cold in the room, and the same thing with the students who are in the class. It's a 2 hours tutorial class. So I started looking more into this, and I've asked our building management team about what's happening, and they said that all of these buildings, or the buildings in our university, is in terms of controlling the air conditioning, cooling, ventilation, heating in the spaces, is based on fixed schedules. So technically, this space is being conditioned, heated or ventilated according to full occupancy. But the problem is there's only 10 people in that space, which is, you can say, can cause issues in terms of comfort, and in some cases, energy waste as well. So this is a big issue in a lot of buildings in our department and also throughout the university. Our buildings is controlled with basic controllers, a traditional system, or PIDs, which basically assumes that the people will come in at a certain time of the day, let's say 7, and then they leave at around 7 p.m. So this is the type of control strategy that we have. And obviously, they want to employ more advanced control strategies, but at the moment, this is what we have in the university. So this leads to unnecessarily overcooling or overconditioning a lot of spaces, which could lead to significant waste in the energy consumption, and also cause problems in terms of thermal comfort. This is even worsened by the flexible working, especially after the pandemic. We have a lot of spaces following the flexible working. We have a lot of staff who are not obviously in the offices at certain times of the day, and this is causing a lot of issues in terms of how do we run our energy system, or cool or ventilate these spaces. So there's a lot of research now with related to demand-driven controls, or occupancy-centric control strategies, which is basically adjusting the set points, for example, of spaces, or the cooling system or heating system according to the occupants number, or the presence in or locations in a specific space, so that it can optimize the energy consumption and the thermal comfort as well. So to be able to be effective, this demand-driven system, or occupancy-centric system, it has to have good information about the people in real time, as much as possible, which is necessary to make those adjustments so that the space, how it's being used, can be fed into the control strategy. So obviously, there's a lot of technologies which can do this. We have a lot of occupancy sensors in the market. We have motion sensors. We have environmental sensors, which is linking the CO2 level or the temperature in the space to the number of occupants. And nowadays we have Wi-Fi and Bluetooth as well, which can link, which is quite useful. A lot of people in the space have connected to the Wi-Fi or Bluetooth to predict the number of occupants in that space. With the increase in computational power and the artificial intelligence, the advancement in this area, plus computer vision and deep learning, nowadays we have a lot of tools which allows us to more accurately detect occupancy in spaces. And this is because of the increase in the computational power resources as well, and also the number of people working in this area, which made it more very accurate. Obviously, it's not only for occupancy, it's a lot of object detection that's happening in the space. So basically, this is through deep learning. I'm not going to go into details about this, but basically, it's a computer model which learns to perform classification according to the images, text, or sounds. In our case, we use images. So if, for example, we want to detect in front of us if it's a dog or a cat, we have to input images of cats and dogs, thousands or hundreds of thousands of images. So with that, we can train this model, and it will be able to, when we deploy it, it allows us to detect what's in front of us. Is it a dog or a cat? So how can we apply this in buildings? So we've started with occupancy first, and we always go back to this diagram here, which shows the heat loads or heat gains or heat loss in a space. And we focus on the occupancy. This is a work done by Dr. Page, who's still working with us in the department. She just finished her PhD. And she's focused on using this technology to detect occupancy in terms of how people are using that space, in terms of where are they, how many people are in the space, and also in terms of the activity levels, because that affects that heat input into that space. So this approach is using a camera, which is obviously quite sensitive topic right now, but I'm going to discuss that later, more about that. So basically, it uses a camera, which is going to detect the number of occupants in that space, where they are and what are the activities. But it does not record, obviously, it does not record the feed, the video feed. What it outputs is basically the real-time information in terms of the heat gains in that space. As you can see here, it changes throughout the day or throughout the time, which is this is what comes out of this device or this technology. There's no videos recorded or images. And this information can be used to control or make adjustments to the HVAC, whether it's ventilation, heating, or cooling, so that we can optimize the comfort, air, the energy consumption. So we've started with a basic test in the beginning to see if we can get it to work. Our objective is to do this in real time, to be able to detect in real time. So we started with training a model with basic images collected from Google or different sources, as you can see here on the left, of people napping, not in that space, sitting, standing, walking. And we started with one person, as you can see in the video here, which shows a person performing different tasks. And in real time, this technology or device is going to provide a heat output in real time. And then we extended this to a larger space, such as an office, which is have multiple occupancy, to test if it can work with more occupants and more activities happening at the same time and in real time as well. And we managed to show that it's fairly accurate and be able to do that. And we've extended it to a whole classroom with about 30 people in that room. And it's fairly accurate in terms of detecting the number of people and also the activity levels as well. So we've managed to, we found out that this is quite powerful in terms of detecting not only occupants and other objects as well. So we've tried to extend the application of this. So now we've tried to, going back to this picture here, we want to see if we can detect more things, so that if we're doing this detection, can we look at other activities happening in that space, such as are the people using the equipment, such as computers or other heat emitting equipment, which contributes to that heat gain in that space or that building, which affects the loads, heating or cooling loads. So in this specific approach, we've used the same methodology, but obviously in this case, we have to train it with images of people using computers, appliances, etc. And here's just an example of how we label those data sets, and we apply it in the same office, which is our kind of a test bed. So we tried to start with basic equipments like computers, PC monitors, laptops, and it's fairly accurate as well in terms of doing that combined with occupancy. I didn't show the combined occupancy and equipment here, but basically we can detect how are the people using those equipments in that space, and at the same time, how are the people are in the space as well in terms of their activities. So that gives us that going back to that real-time information. So if you can imagine, if you're modeling a space in a energy modeling software, you're probably going to use a more fixed or constant profile, such as the one you can see in red. But in reality, the profiles or real-time information in the space is more of the blue based on the detected information. So that's the heat gains or heat output emitted into that space. So that correlates to the different activity levels that's happening in space in terms of the equipment. And we've run it through a energy modeling software to see how much can we actually save by applying this technique. And so if we compare that with a typical profile that we typically use in a energy modeling software compared to this more accurate real-time information, we've managed to save some energy in terms of cooling loads and during the summer and also in the winter as well, which is the opposite actually. We use more energy because it tried to have a higher thermal comfort level in the winter, which provides more heating because we have less people in that space, which is obviously its aim is to balance that energy consumption, energy efficiency, and also the thermal comfort. So now we've shown or we've seen the capability of this technology or computer vision, and we've tried to further test other things. What else can we detect in this space, and how can we help control the operation of the building according to this information that we can get from this. So going back to this classroom that I was teaching in, this is another particular day, and this is a typical issue that I've seen in a lot of these spaces that we have in our university. So typically in the winter, even in the winter, we have openable windows, and the users, which the students, lecturers, they tend to open the windows during the class. And this is to provide fresh air ventilation in the space. Even though we have air conditioning, they would still open that. And the problem in the winter is obviously we have to heat these spaces as well. And if we have these windows open, that heat will obviously be escaping. And so that we have that heat loss and we have cold air going into that space. So this leads to waste of energy if we don't optimize it, especially during times when there's no people in this classroom and there's no class. This is happening throughout the day. And what's worse is when people is finished and completed the class, they leave this room and they don't close the windows. They keep it open. And typically after 5, this is one of the class I've been in, when at the end of the day, all the students left and all the windows are open. And the heating system has to run throughout the day. I mean, until 11 p.m. So from 5 to 11 p.m., all these windows are open. All those heat is being lost in that space, from that space. So this is why we have a lot of ventilation heat loss. This is one of the significant sources of heat loss in buildings, at least in the UK. And this gave us an idea to use the same approach to find a way how we can save energy or reduce this or minimize this issue. Obviously, what we can do is try to not have ventilation or openable windows in these spaces, but it's not possible because we need to make sure that we have good ventilation in this space, especially during the now with the concern about raise awareness about the good indoor air quality and the transmission of virus and pollution. So we have to keep a certain ventilation of fresh air into these spaces. Obviously, we can have sensors in each window so that we can make alert or inform building service manager or the people who are particularly looking at the building. The problem with sensors is if we have in this specific class we have 20 windows, we'll have 20 sensors, and that will be all there'll be more in all the other rooms, and that could be an issue in terms of batteries, maintenance, etc. So what we thought is, why can't we use the same approach? So if we're using this detection system, which can provide us information about the heat input from occupants and equipments, why can't we use the same approach to detect the open windows as well, or closed windows? So we've tried to see if this will work. And we started with labeling basically open and closed window, which we got from online, and start trying it. And it didn't work very well at the beginning, as you can see in here on the right. It detects some open windows, some it doesn't detect. So we tried to try a different approach and different types of configuration, how we label those data sets. And if you look here on the right, this is something that worked, which is just labeling those openings. And with this, it managed to provide a more accurate detection of the open windows. I'm not going to go to show the entire video, but I'm going to fast forward. So I just want to highlight that the issue is when, for example, at the end of the day, when the occupants finish their class or using that space, so they leave the room and they close the lights or switch off the lights, sorry. Then this room during the winter will be emitting all those heat that's generating by the heating system. So that is, that heat is being wasted. There's nobody in the room. All the windows are open, and the heating system will run until the end of the day, is about 11 p.m. And this is an issue that we want to solve. So we've tried to create kind of a framework how we can apply this by using this detection system, which can detect occupants leaving, for example, and the windows open as well. And this will allow it to detect this issue and create those profiles as well at the same time. And it can ask the control systems to switch off the heating to avoid this or minimize this, or it can send alerts to building managers or building users so that they can switch off the heating or close those windows so that you can minimize the ventilation heat loss. So what's next? So we've tried to apply this in different cases as well in the indoor space or indoor environment. We're not only looking at energy efficiency or thermal comfort, we're also looking at how can we use this to enhance indoor air quality. As we know, in spaces, we obviously do a lot of cooking. You can be doing a lot of cooking or doing activities which is leading to a lot of pollutants, such as when you're using the stove, the oven, using the toaster. So this is leading to obviously pollution or pollutants in that space. And what we thought is, can we use this detection strategy as well to detect these activities and use this information to control the ventilation system or the extractor fan in real time so that it can react very quickly. So when you're doing cooking, it can switch on the ventilation device or increase it or decrease it so that it can balance the ventilation heat loss that I've been talking about and also the indoor air quality in the space. So in here, we just did a very simple test to show when a person is doing multiple things in that space. We've recorded the air quality as well, which is different configuration where we apply windows, ventilation, no ventilation, to see how we can use the detection strategy to influence the operation of the ventilation systems. So it can also work in multiple zones or multiple rooms, and it can obviously control the ventilation in different areas depending on the number of people in that space, so that you can maybe have higher ventilation in more people when there's more people, to less when there's not many people in that space, and switch it off when there's no person in that space. Another one we're trying to work on right now is to see if we can detect clothing level of people, which is, again, a bit quite privacy invasive right now, as you can see, but I just want to demonstrate that how can we use this to detect if people are wearing light clothing or heavy clothing. So this is not to detect what people are wearing. It's to use this information to better predict thermal comfort in a space. So now we can detect the activity level using same approach, like sitting, standing, walking, which have different heat emissions. But at the same time, if we can detect the clothing level, such as light, medium, heavy, of the occupancy, we can probably have a better prediction of the thermal comfort in the space. And it's not only to detect what they're wearing, but it's the changing as well. So you can see a person is changing from light to from heavy to light, and how can that influence the thermal comfort in that space? How can we influence the calculations or prediction for thermal comfort in that space is something that we're interested in as well. So that's one of the ongoing works. I'm going to speed up a bit. So I don't know if that's playing, but so one of the other things that we're looking at is how can we. So now we're trying to enhance the energy efficiency of buildings. We're looking at thermal comfort. We're looking at air quality as well. And how can we use this method to also improve the safety in spaces? So obviously, detection, computer vision has been used in fire detection in many research, mainly for outdoor spaces like the forest fires, etc. So we tried to apply this as well in indoor spaces to see can we detect or quickly detect the fire happening in the space quicker than smoke or smoke detected provided by detection system. So I wanted to show that it's pretty quick as well in terms of detecting that. And going back to that kind of all-in-one solution that I've mentioned before, what we're trying to do is to apply this technology so that it can perform multiple tasks. So it kind of an all-in-one system or solution which can do all of this in indoor spaces. So we can have a healthy, energy efficient, thermal comfortable, and safe spaces for indoor environments. Obviously, there's a lot of things to be done to get it to work in real or in practice. So one of them is to connect this in real buildings, such as with the BMS. So now we're talking with the estates team in our university to see how we can apply this in some of these bigger classrooms and see how we can connect it with the control systems or control strategies of those spaces. And the bigger issue that we always get when we present this in conferences or in meetings is the privacy and security concern, which is obviously a big issue around the world, but especially in the UK with the GDPR and privacy laws. So this is always the question we get. So we are trying to address this by the images that I've shown is obviously from personal cameras. I mean, normal cameras, which give you the full information about the person. But as I said, it doesn't really record the person. It provides those data. The output from this technology is the data or the values of heat gains, for example, or the thermal comfort. But we're exploring how we can apply non-invasive vision-based methods such as thermal camera. And we've managed to show that it's fairly accurate as well in terms of detecting the occupant. So we're trying to move on to those types of technology so that we can address this issue. So just to quickly summarize, I've shown how we can apply a vision base to aid the demand-driven control of buildings. I've shown the issue with using static or fixed schedules controls, which can lead to over or under conditioning of spaces. And then occupants And the target is to have an all-in-one system that can provide a balance between energy efficiency, thermal comfort, health, and plus the safety as well. Thank you very much. Happy to answer any questions. And I put the email and the website as well if you guys are interested. Thank you.
Thank you, John. Yeah, the right website is your company, right?
Yes.
Cool. And yeah, finally, we will have a Q&A, yeah, for your 3 presentation. Okay, so thank you again, John. So let's move to our final presenter, Baojie. Yep, Baojie from Chongqing University, and his presentation will present smart mitigation and adoption decision support system to overcome the challenge of lack of knowledge and professionals in actual implementation. His presentation will introduce the causes and the impacts of urban heat and the stress to sustainable development goals in order to demonstrate the urgency of dealing with urban heat challenges. Yeah, Baojie. Thank you, Baojie.
Thank you so much for your invitation. And so, hello everyone. Yeah. So it's my great pleasure to share my latest research on the smart urban heat mitigation and adaptation decisions. So let's start. So basically, the background of this topic is on the climate change and also the extreme heat and the heat island, as Professor Huang Jianxiang had mentioned this. So I would like to highlight the disease caused by the extreme heat, especially for the safety and the health consequences associated with the urban heat. So 20 years ago, in 2023, in Europe, so about 2 weeks, the summer extreme heat causes about 2,000 deaths in just 2 weeks. So after 20 years, in 2022, also in Europe, in June, it causes about 60,000 deaths in also about two weeks. So we have many other significant extreme heat events in Asia, in Southeast Asia, and in Russia, and so on. So we need to consider how to address the extreme heat events. So and for China, we have there have been some studies on the prediction of the future urban heat challenges. So according to the RCP 8.5 scenarios, it's estimated that by 2030, there will be 10 million to 45 million people under the threats of the extreme heat. But by 2050, this figure will increase to 110 to 250 million. So the extreme heat also causes the significant economic losses and about $1.5 trillion every year by 2050. This is especially for in China. We can see here in the lower rights in the lower reaches of the Yangtze River, especially here and here. So another challenge is very common for all cities over the world is the heat island due to the use of the building materials and road materials and the reduction of the green and blue infrastructure in cities. And also Professor Huang Jianxiang has mentioned that the use of HVAC systems and also the ventilation reduction due to the increase of the building height and the building density. So I would like to highlight the synergies of the heat waves in the heat islands. This has been neglected in the past studies. So according to our studies in Shanghai, we found that during the heat wave period, we found the heat island effects can be amplified by 1.5 degrees C. And also another challenge is the co-occurrence of the heat wave and the drought. So according to studies, it's found that their co-occurrence is increasingly frequent at 10 to 11% per decade. So it is well known that in 2022, in Sichuan province and also in Chongqing, the city I'm in, so we found the drought of the Jialing River, which is one of the bridges of the Yangtze River in China. So about the impact and rates of the of the urban heat, we find that the temperature increase is the phenomenon, but it causes the energy and the water use increase, and also the work productivity reduction, and the reduction of the thermal comfort, and the increase in the morbidity and the mortality. So if we want to see it in a broader scope, we find that heat wave or the extreme heat has causes many significant environmental, agriculture, transport, economy, and health impacts. So beyond this, we think about how to link this urban heat with the SDG, and we find that the urban heat is widely associated with 17 goals defined by the United Nations. For the no poverty, we find that increased urban heat without cooling preventions is linked to lower productivity from land and income. But for the poverty areas, people do not have the cooling systems to alleviate the heat it related impact. So we find that there is a positive cycle. So particularly, we think the urban heat in terms of the sustainable cities and the communities, the Goal 11, and the climate action, Goal 13. So we combine them into the cool cities and communities. We would like to use the urban heat mitigation and the adaptation strategies to address the heat challenges, to create the climate inclusive and climate healthy cities. But when we develop the cool city and communities, we have to highlight some information. In the past, we think the urban heat is just a meteorological problem. So in recent decades, we find that the urban heat is the environmental problem. But we have to say that the urban heat is a social, economic, and health problem. And in the future, if we would like to integrate the urban heat into planning and design practices, we have to encourage government or to push government to develop different tools and the policies. This is, we think, is a policy and a decision issue. So, so how to address the urban heat challenge? We say we need to integrate the urban heat mitigation and adaptation sciences and the technologies into urban planning and design, because planning and design is to actually modify or change the cities for the more comfortable and heat resilient environment. And so for the extreme heat, it has been recognized for thousands of years, and for the heat island effect, since Howard recognized that in about 1810. So it's more than 200 years. But what's the progress on the urban heat mitigation and adaptation? So we have done the literature review in the studies of the urban heat mitigation and adaptation in the past 30 years. We found that the urban heat studies has been focusing on the urban heat island impact assessment and the cost identification. And many scholars have also are working on the microclimate regulation and the human thermal comfort assessment or modeling. And for the atmosphere research, all the occupational health studies, they are working on the climate-related health impact and adaptation. So some studies, some researchers in Australia, in America, are working on the development of the mitigation strategies and techniques. But we believe that's not enough to enable planners, designers to implement the urban heat mitigation and adaptation. So we want to upscale it into a city action, in like what we have done, like the low carbon eco city or the smart city. That we would like to advocate the whole city, the whole cities to work on the urban heat challenges. So how to do? First, we think it's necessary to understand urban heat within a broader scope on its impacts, not only in the environment, but also in economy and in health and in the social. So based on this, we can arouse awareness and knowledge of different stakeholders, like the government, like enterprises and the general public. Another thing is to upscale it to a open heat action. So not just from the body thermoregulatory and microclimate studies, we want to upscale it into a CT companion. So how to actually address this? So there are some solutions on the heat preparation, mitigation, adaptation, and also the adoption of the co-benefits approach is like to release the multiple benefits of many sustainable initiatives in cities. But currently we are facing several challenges like the lack of knowledge, lack of awareness, lack of the professional staff to address the urban heat. So how to address these challenges or barriers? We would like to develop the decision support tools to close this gap. And this is what we want to see, the smart management or smart mitigation and the adaptation decisions. And then we need to identify more barriers and to plan for the future work. So this image shows the framework for how framework on how to counterbalance the urban heat challenges. So before introducing the framework, we need to highlight the goals and targets for the coastal communities, because at present we do not have enough concern on the targets. And we would like to think about how to make sure the thermal comfort to guarantee the thermal safety and the thermal resilience. So to meet this outdoor thermal comfort is the most aspirational target for us, because during the extreme heat it's very difficult to achieve the very comfortable thermal comfort. But we need to achieve the thermal safety and to protect people's health on the extreme heat, and also to ensure the thermal resilience of the city. So to make sure the society can respond to withstand and to recover from the heat soon. So on this framework, like Professor Huang Jianxiang's top-to-down, or top-to-down, or the bottom-to-up strategies, we have the policy-driven, and also to develop the guidance, laws, and rules and regulations for the government and the enterprises, and also to increase the economic investment to encourage or to enable the government, also the industries to work on it, like to collect the funds also to develop the incentives and also to calculate embodied returns. And for the techniques, actually at present we have the mitigation and adaptation strategy, but we would like to broaden it to a sound prevention system and also the post-heat recovery system. And also for the co-benefit approach, as Professor Huang Jianxiang has mentioned, the green building, and using the green building to mitigate the urban heat. So, and it's actually to use the multiple benefits of the existing sustainable initiatives, like in China, we have the smart city, and in Australia, the water sensitive urban design, and so on. So another thing is to ensure the public to have the knowledge and the awareness to protect them, and also to enhance the capacity of the government and the industry to act. Yeah. The next one is on the how to integrate the mitigation and the adaptation strategies into the real projects. So if we have one TOD precinct here, and this is the new project, so what to do? The first one we think is to assess, to map, and to identify the heat-related impacts, as well as their time, duration, and the location. So we have many methods or techniques to capture the heat spots, but we would like to highlight the temporal impact, because when people are outside, they may feel comfortable in the short term, but once they are outside for 15 minutes or 20 minutes, they will feel uncomfortable, or the heat will threaten their safety. And based on this, once we identify the hotspots, and then we tailor these hotspots into the context, and then we develop the combination of the techniques or the individual techniques to preliminarily inform the urban planners and designers how to address the urban heat challenge. So this is the first step to close the gap. And then to run the simulation to assess the performance, the cooling performance of different mitigation strategies. And if they can achieve the best performance, so we can prioritize them into the government policy or the planning practices. But it's very difficult for us to address the urban heat, to reduce temperature to about 10 degrees also, or to improve the summer comfort significantly. So we highlight the importance of the adaptation strategies, like we need to identify the walkable areas or the heat resilient areas to tell people when to go these areas, and also where are the destinations and so on. So based on this, we would like to protect people from the heat related health issues. So next one is on the urban heat management plan. So actually, how to do this is this image charts the how to transform, how to pass the urban climate sciences and also mitigation and adaptation technologies to the planning and the design practices. So we defined the components, like the first one is to identify the urban context, to identify the heat release rates, to set up the goals and targets, and then on the technologies, on the mitigation, adaptation, and also sustainable actions where the co-benefit approach. Then we need to assess the suitability, feasibility, and also the performance, and then to set the planning and design and the management schemes for implementation. Basically, we have also defined the stakeholder of each component to close the disputes or the conflicts of different government or the enterprise departments. So this is try to determine the responsibility of the different stakeholders. So next one is on the heat assessment. So here so it's important to assess the heat. So previously we have many indicators on the microclimate, on the temperature, relative humidity, wind speed, wind direction, solar radiation intensity, and so on. And also we have some indicator to assess the urban quality, like heat island intensity, and also the white dryland intensity. But here we would like to emphasize the environmental indicators, economic and health indicators. This is important to convert the urban heat, like the meteorological concept to the environmental economy in the health concept or the philosophy or the practices. So, and what kind of strategies or the techniques we have here? And previously we have many strategy on the cooling techniques, like the planting trees or the design the water bodies and use the reflective materials. But here we define the heat resilient infrastructure. We expect the society can withstand, respond to, and recover from the heat-related impacts through a series of actions like the planning, design, construction, and the operation and the maintenance, and so on. So for the heat resilient infrastructure, it consists of the structural measures or the non-structural measures. For the structural measures, it's not just the mitigation and the adaptation. It also includes the monitoring and the warning. Here we advocate to convert the climate indicators to the heat health and to tailor them to the different demographical characteristics and the different urban contexts and the drop taps and so on. So here we have the ICT systems to transfer the information from every stage to next stage, from different group to another group, and so on. And for the non-structural meters, is like to the awareness change, the knowledge improvement, and also the change of the operation and the change of the behavior, and also the gas and the plans and the policy and the regulations and so on. This also to pass different information to different holders, different paths associated with the urban heat challenges. So the next one is on the urban heat mitigation and the adaptation system. So this work is what we done. So what we did in USW Australia. So this is like to link the different techniques to the different urban contexts to tell the local planners, designers, and to tell the local governments. So the basic strategies they can use to address the urban heat. So we have the cooling South Melbourne and get to the urban cooling strategies. The strategies are tailored to the different cities like the Darwin and the Brisbane, and also Melbourne, Sydney, and also Adelaide, and so on. So we have also developed the cooling Sydney strategy planning for the 2050, and also the cooling Western Sydney, and so on. And also for the decision support tool, this is developed to address the gap of the lack of the knowledge, awareness, and the professional staff. So on the heat island mitigation decision support tool, this is developed by the UNSW team. So basically, and we have a project. So just so the planners, designers just select a different kind of the mitigation strategies, and also to link to the green star and the green star of the buildings and also the low carbon eco cities. So they can select the different levels of the strategies, so we can visualize the different types of the performance, and also we can calculate the average. Maybe the temperature reduction, and also some comfort improvement, and also water and energy saving, and so on. So this is important to close the gap to narrow down the knowledge gap or the technical barriers. So another one, if a staff do not have any knowledge on the urban heat, this is particularly true for the local government. They do not have knowledge on this. So for the government or the third party for the assessment can tell the basic project information, and also climatic background, and also on the geographic context. So based on this, this system can extract the surface characteristics or the space or the morphological characteristic of the project. So they can match different kinds of strategies or the techniques, then to use the genetic algorithm to optimize or to select the best combination with the techniques for use. And also it can link to the environmental and the social and also economic indicators to see which variable has the significant impacts on the performance, and so on. So another one is on the adaptation system. This is what we are doing in Chongqing University. So basically, we would like to use this system to tell people in their daily life when they are facing the extreme heat events or the extreme heat challenges. So what they can do to address or to avoid the heat related threats, and also where they can go for the daily recreation, and also when to do and how long they can be outside, and to avoid the heat challenges, and how to do. So there are 6 components in this system. Basically, so the first one is about the data collection. So on the data collection is like the urban morphological characteristic and the weather information. So we run the simulation to estimate the heat the heat-related threats of next day or the future, and also to convert this data into the thermal or the thermal health or heat health or heat safety data, tailoring to the different demographic characteristics and also job types. So we can store this information on the platform. The people can retrieve this data and use their phone or the web page, and so on. So also we can also analyze the key challenges, the key hotspots in this area to add some cooling interventions through the planning and design interventions. And also we have a case on the walkability of the offset, because the walking is a very often daily functioning. And also is people have to walk from their home into the bus station or the train station, and to when they go to work, and also when off work, people have to walk from the bus station or the train station to their home. And people have can't avoid extreme heat through staying at home. So based on this, so for this we have full drivers or the factors on the climate or the weather background, and also the urban morphology characteristics, and also the demographic features, and also the health and the safety values. And this is a threshold to screen. So which value is which value is safe for people. So based on this, we have the urban heat or the threats or the urban heat health map, and based on this, we can identify the adaptation facilities for or the services for the public spaces, and also to tell people and what they can do by themselves, like to wear the cooler clothes, and also to use the umbrella to avoid the heat, and also to add different cooling interventions into the precinct or the neighborhoods. And also we have a very simple case here, and from point A to point B, and there are several roads, and which one is the best. So it's very difficult to justify if the precinct is very complex. So here we developed the models to run the simulation and to compare to calculate the thermal comfort or the some health issues, and also to screen and to compare which one is the best. So here we actually to use the two indicators to screen the walkable roads. The first one is to compare, and the second one is to use the transient heat tolerance of the bodies, and also the cumulative heat tolerance of the bodies. So once this value is doing the heat tolerance, we see this road is not walkable. And also, and we have a case in Mianyang in Sichuan province is about the planning of the 15 mini cities. And so in this case, there are 12 neighborhoods. And so basically we simulate the heat stress when people walk out the main gate of the neighborhood and to about 1 kilometers, about 15 minutes. So we see the remaining heat tolerance of the bodies. So like this, so is for the green is the remaining 40 or 45 to 60 minutes. And also this is the assessment for the 12 neighborhoods. So based on the population density, we weight and so generated the total or the overall heat tolerance of the 15 mini city. So for the green areas, we find that this is the thermal comfort or the thermal tolerance for the citizen, for the local residents. So we can plan the most frequently used services or facilities in that area to avoid the heat threats. And also for the purple areas, we can plan and least frequently used infrastructure here. Of course, we need to add some adaptation or the mitigation interventions in this area to break the heat stresses in this area. So people, when people face the heat stress, they can stop here, like the cooling centers or the shelter and also water refill station. They can recover their body and then to walk to the next station. And also we developed the heat resilient education precinct based on the Chongqing University. These are the components. There are the components of the preparation, mitigation, and adaptation, and also to the information sharing platform in the assessment, and also to the heat action plan, the post assessment. And also we identify the walkable roads for the students and the staff when they walk out from the dormitory to the office or to the classroom, and also to identify the hotspots on different roads. And also another one is and also in Chongqing University, you can see here in the way. So there are two tasks. The first one is to mirror the heat tolerance of the bodies of different people, like the male student or the female student, and also the different age of the people. And based on this, we developed a threshold, and then to identify which routes is walkable. Based on this, on the June 11th of the 2023, this is the normal heat day, and also for the July 10th is the extreme heat. So the heat wave day, we can see the paths and the different kinds of the heat stress for people, for the students and for staff. And based on this, we can also identify the hotspots in these areas. So we think about to convince the university or the university managers to add different mitigation interventions to lower the small stresses or heat stresses in this area, and also to share the different information to the students, like based on the information system. And also we are working on the readability, accessibility, interchangeability, and also the workability, and to assess the heat stress, tailoring the different kinds of activities and in different areas, like the sporting course and also the walkable roads, and also when people on the grass, or when people are working on these areas, or like to assess the heat stress and to tell people and the time for their activities and so on. Yeah. I think that's all my presentation. Thank you so much.
Thank you, Gautier. Now there is any questions for our three presenters? You can type or just open the mic just to ask.
Question.
Yes, please.
Oh, okay. So for Professor Huang, the question is, I was deeply impressed by the work on how to spell that, Kowan urban renewal, right?
Yeah, it's
yeah. This project. Yeah. I remember your discussion on the integration of top-down and bottom-down approaches as policies and guidelines for planning the entire community. However, I have the concern regarding the comprehensive nature of planning, which includes considerations beyond just the environment, such as culture, demographics, and human behaviors, while the bottom-up approach based on the big data generation often focuses narrowly on the study topic, such as using only specific environmental indicators for the guidance. It may overlook potentially disruptive impacts on other factors, such as the layout of residential units, as you mentioned. So the question is, how do you balance the situation, particularly in terms of rearrangements, the top-down and bottom-down approaches?
Well, thank you very much, Melody. You brought a very important point. I don't have time to introduce the process because we have conducted quite a bit of a community engagement, and also the Urban Renewal Authority in Hong Kong. We do this roadshow, we do this extensive, let's say, community survey, and also the charrette is the French word for sort of a co-design. And then we sort of ended up with a central green space at the heart of the community, at the center of the 7-hectare site. And then this is something that community would like to spend time to gather. And this is elderly would play Tai Chi, and people meet together. So really, it's the southern China, the cultural practice is demonstrated there. And I think their concerns actually primarily is sort of there's really lack of high quality, enjoyable open spaces for the community. There's a lot of people actually express these concerns. So I think in response to that, so we boil down to air quality and thermal comfort as one of these priorities, actually stemming out from this the bottom-up grassroots concern. And there's a lot of more stories I can tell you, but you're welcome. Actually, perhaps we can sort of communicate via emails. You can also get my means of communication through Professor Yao Jiawei, if you want. And then you also asked about the multi objective balancing. Yes, I think that's where we're heading to, and we have to, as planners and urban designers, we make decisions not only for heat, although it's very important, but we also have to, with regard to daylighting, to views, to sort of pleasure derived from tranquility, to fresh air. And I think fortunately, we have more tools that allow us to quantitatively assess these, and perhaps to combine with optimization algorithms, we can sort of bet on that technology can give better and better suggestions. Just like ChatGPT can give you a hint of maybe a good piece of writing, a good PowerPoint slide, or just a good image might look like, but it's probably not going to replace a brilliant writer or a great designer. They can still make the right decision that's innovative, that's far-sighted. Yeah, we'll be happy to continue the conversation if you want to really get in touch afterwards. Thank you again.
Thank you,
Thank
Professor
you,
Wang.
Professor
Thank you, Melody. Yeah. Yeah, if you need, I can send Professor Wang's WeChat to you.
Yes, I need.
Okay.
Is there any
So-
potential to use such as big model for artificial intelligence to control all the factors in to like arrange the planning? Is there any potential for the big model?
If you're asking me, I think
Yeah.
my estimate is a bit pessimistic because our domain consists of largely poorly organized data sets. So unlike, let's say, large language models, you have the entire internet that's digitized, standardized, and it's clean. But our domain knowledge really exists in such a fragmentation. You can only interview, you can sort of read the books from great designers and architects and practitioners, but not everything is organized nicely in the library. So I think we probably still have to figure out a way to bypass these barriers. And that's why I think all these approaches, the model demonstrated by the other professors today, John and Baojie and many others, that's so valuable. Because actually we're trying to bridge those barriers that we're not yet at the stage that a large model is going to put everybody out of job. I think fortunately we're still providing these useful insights, but I think we're really at the stage for big change. Major change is coming at us.
Thank you, Professor Huang.
Thank you for the question.
Yeah, a question for John. Yeah. From Jingyu. John, and he's quite interested in your research on the deep vision enhanced HVAC control system, and he said he would like to ask that if it is needed to run targeted simulations, considering energy consumption and thermal comfort prediction for each building space, with different equipment and space features, and how do you consider the use generally of this vision-based control system, especially on the emergency of general artificial intelligence?
Thank you, Jinyu, for your question and your interest. So the results that I presented there is yes, it's linked with energy simulations. This is to only show the effect of using this approach or detection approach on the energy consumption, thermal comfort, air quality in the space. But in practice, what we're trying to do is to have this detection system to be directly connected or linked with the control system or the BMS or whatever is controlling the energy system of that building. So it's not required to model the building in this case. It's directly going to be connected to the control system to make those necessary adjustments so that we can optimize the energy, thermal comfort, air quality, etc. And in terms of the generalizability of this, we've tried to use the same approach or method or algorithm or trained model in all types of spaces. So we managed to try it in offices, in classrooms, in public spaces, and in hallways. So the same model that we've trained, we don't need to train it for different application or different types of spaces. It will be able to detect the occupancy in this different location or spaces. But obviously there will be certain types of activities that we need to add some data so that we can get it trained for those situations. But going back to the building energy simulations, one of the potential application of this as well is to feed into directly to the energy simulation of buildings, which is an issue for us when we create models for certain buildings, is the occupancy profiles that we use is very steady or fixed, which is not very realistic or does not represent the real usage of spaces in buildings. So we're looking at this area as well. But yes, thank you for your question. I hope that answers the question. I'm not sure, but yeah.
Thank you, John. Thank you, Jinyu. And another question for Professor Huang. Yeah, attended your lecture earlier and was fascinated by the software you developed to calculate the environmental benefits of trees. I have previously used the EnviMat for similar assessments, but it tends to be quite time-consuming. Could you please share with me how efficient your software is compared to EnviMat? And I'm also interested in knowing if your software is open source. Thank you for your time and attention.
Okay, thank you, Yenting. If you send me email, I will just email you the software. We wrote from scratch. I think our software actually fortunately runs a bit faster than EnviMat, and is robust, is reliable. I think it's based on first principles, and then there's necessary sort of assumptions or simplifications, such as we have to relax the momentum conservation equations, for instance. There's many literature saying that how this is cost effective in terms of state-of-the-art safety tools applied to outside or urban configuration. And then sometimes you really have to take a trade-off because usually our clients or policymakers are very impatient, they're very busy. As researchers, we can wait as long as necessary for a good piece of research, but practitioners really, all they have to do is to make decisions when there's insufficient amount of information. So yeah, I'd be happy to send you that piece of software and have fun with it, and then you can actually compare with EnviMat and let me know. Thank you.
Thank you, Professor Wang and Yanting. Yeah, any questions? Yeah.
Hi.
Yeah, yes, please.
Yeah.
Yeah.
Thanks for the professor's wonderful lectures. And I have a question for Professor Zhong. Yeah, Professor Zhong, I'm still here.
Yeah, John is here. Yeah.
Thank you for your very inspiring lecture, and I actually have a question about the payback period, because I know you have a company, so this methodology will push us towards the application of the building management system in the future. Yeah, we can see the potential, but now there are still some barriers, like the privacy of the users, especially when you install the monitor, and then the payback period, because we need money to buy those monitor like sensors, and then we save the energy. So it's just like we invest and then we save money. So as a user, we usually consider about the payback period, like the business potential of these methodologies. So yeah, this question, because our group are also doing some similar topic in China, but yeah, it's still a little far away from apply this methodology in the real buildings for us. And yeah, it's very happy to know that you have a company. So I'd like to ask you some information about those business thing. Yeah.
Thank you very much for your question. Yes, it's very important to think about the in terms of the cost effectiveness of the technology. Just to make you aware, we haven't really commercialized the detection approach in our company. We're currently the products that we have there is based on our low energy ventilation technologies, but hopefully at some point we'll be able to get there. But just to go back to the question about effectiveness of the device, in terms of cost analysis, we didn't really do a detailed analysis of the payback of this technology because I think in terms of the actual camera itself, the camera itself is very cheap. You can look at your webcam and how much it is. This is the exact technology that we're using. So in terms of the detection approach, it's quite a low cost. The issue is the privacy that we're trying to solve now. So we're trying to look at more less privacy invasive techniques like the thermal camera, which can be more expensive. So we try to develop a low cost thermal image system so that it can make the users obviously not in the video because that's the main concern, and at the same time to make sure that the cost of the device is low cost. But if you can imagine the device that we're trying to develop is to we're going to replace all sensors in a building, but it could potentially aid the sensors that we have so that we can reduce the number of sensors or be able to save cost that way. But we haven't really we haven't done a detailed cost analysis because I don't think we're there. We are at the early stage of the development, and hopefully we can get it into a product at some point.
Yeah, thank you for your answer. And I still have another question. It's about the data because in this area, the progress is like to predict then control, right? To know what the environment is like in next step, time step, and then we have the ability to control it better. So this process needs a lot of data to support our decision. So yeah, it requires a lot of good quality data. But the data of different buildings, like different rooms, they are totally different. So when we apply this methodology to a totally new building, how can we predict or to gain the data before we install this device or equipment?
So the detection device works in real time, although I know there's other techniques there which monitor spaces using basic sensors, which collects data for certain buildings and translate this or use this to predict other buildings as well. In this case, it will be installed directly in that specific space or building so that it can learn or predict or understand how this space is being used, and directly it will control the building or the systems or operation of that building in terms of the systems. But it works in terms of if you will use this same device in another building, it will be able to detect its to carry out those tasks such as detecting the occupancy or the use of equipment, because the input data or the training data we use is based on large collections of images from the internet, from different sources of people doing different activities, so that we can be able to apply it in different buildings, whether you're in a kitchen, whether you're in an office or a residential building, or in your big lecture theater, that should be able to do it. But if you're talking about the control, the the system, then that has to be developed. We haven't really developed that yet, but yeah, that is our future work.
Yeah, thank you for your answer. It's so inspiring, you know. Our group is also focused on the very similar topic like smart control, and hope we can have the future communication after these lectures. Yeah, thank you very much, Professor Zhong.
Thank you for your question.
Thank you, John and Liu Xin. Any questions? Any questions for Baojie?
I have another question for Professor He.
Okay.
Yeah, thank you. I was really impressed by the Professor He's lecture, and especially the workable community. That project, I'm really interested in that. And your establishment a really comprehensive system for workable and predicting pedestrian walking experience. However, I think walking is a really deeply personal experience, influenced by many factors such as perceived temperature and other environmental variables. In your system, do you envision integrating personal experiences with environmental indicators in the future? And can these two aspects integrated each other and to support your future framework? And how do you plan to collect the necessary data for the such integration? I will know more about that. Thank you.
Yeah. Thank you for your question. So it's a very important question because we in the future we need to tailor to the system for the different individuals. At the present, we have developed a very simple model and all the system at the very early stage. Currently, we have just two key things: is to generate a system to generate the recommended like the suggestions for the pedestrians. And also we have linked that to the demographical characteristics like the gender currently, and also for the age. And but it's very difficult to include more indicators at the current stage. But it's important to integrate, and also because we have people have the different behaviors and the different individual characteristics like the clothing, and also people may use the umbrella, and also they have the different maybe the activities intensity, and also many others. This can actually affect the walkable roads identification. But at the present, we have used the very, maybe we call it maybe the least or the most or we can use it like the most strict way, and to control and to make sure all people on this road can be safe or can be healthy and can be the heat threat free and so on. But if we would like to control that in cities, is quite difficult, because in cities we have so many people, maybe for many people in other suburbs or in some district walking in. Like in China, we have the city walk, and maybe you are maybe a tourist or the maybe in the local tourists or the maybe the intra-province tourists and so on. They may be here, and they also have the maybe the like the heat adaptation capacity or the heat resilient capacity can be different. So this is also affect addressing the maybe the local system development. But currently, we would like to develop the framework, and then can generate implementations for the local government and for the planners, designers. In the future, if the community for many communities or neighborhoods, if the maybe the like the stakeholders or the owners, they would like to develop a more accurate or the more and also the models with the high resolution. I believe in the future they can do that. Yeah. Thank you so much.
Thank you. Thank you for your answer.
Thank you, Baojie and Melody. Any more questions?
Hi, Professor Baojie. I want to some question for you. I'm interested in your discussion on climate adaptation strategy at urban scale. I have some conducted relevant research focusing on the architecture scale. I have some inquiries, so I would like to seek guidance on whether strategy at scale, urban scale can be further transformed to smaller scale, such as architecture, the more smaller spans, and how one might approach for this transition in thinking. Thank you, Professor.
So yeah, so for question is how to transfer the urban scale to the local scale or the building scale.
Yes.
Yeah. Yeah. So currently,
For the interior scale.
Yeah. So currently, we actually think we can think about this question from different angles. Yeah, the first one, and we are working on the guidelines for the architecture and for the architects and all the building designers. So basically, so it's at an urban scale we can have, so there are so many very general strategies, and also at the urban scale we have maybe to plant the trees and to improve the greening ratio. But at the architectural or the building scale, there are so many techniques, and like on the facade or the roof, we have the green roof or the cool roof, or the green facade or the cool facade, and so on. As the maybe around the building, we have also the cool road or the permeable roads and so on. So we are working on the guidelines to tell people and to tell the building designers to select to which one can select, tailoring to the surface or the morphological characteristics of the buildings or the roads and so on. And another thing we are thinking about is how to integrate the building function or the urban function, especially for the plaza or for the commercial buildings or the residential buildings. So tailoring to the functions. Yeah. So actually, from the urban scale to the local scale, or and also to the microclimate or building scale, there is more complex. It should highly respect the building features and also the building functions and so on. Yeah, thank you. I'm not sure if your questions answer.
Thank you. I want to more communication with you. Thank you.
Yeah.
Thank you,
Yeah.
Baojie.
Hello. Yeah.
Yeah.
Hello, Professor He. Yeah. I have questions. Yeah, we all know that the heat waves can cause some significant harm, especially to some maybe low-income groups. So how can we achieve a balance between the government, business, and the individuals in the mitigation strategies?
Yeah, it's a very important question, but it's also very difficult. Currently, we have communicated with the government. We would like to push them to address the urban heat challenges in cities, because if the government can put some energy or put funding and also the incentives to this, so the enterprises or the industry will do that, and also then for the general public, they may get some benefits, because in China we have many the older residential areas or the urban renewal. Also, they can get some chance to improve the quality of the living quality of their residential and so on. So I believe we need to try to push the government first, and then to attract the industry. And then if we just depend on the individuals or the public or the especially for the low income groups, it's very difficult to get enough power or the enough energy to address this challenge. Yeah.
Yeah.
Thank you.
Okay. Thank you. Thank you.
Thank you, Baojie. Is there any more questions? It's a busy part for Q&A here. Okay. If not, yeah, if you have any questions, you can tell me, and I can send our 3 presenters email to you, and you can have further communication. And it's a time to end our today's academic event. So let me see. Before we as we come to the end of our conference, I would like to express my heartfelt gratitude to all our speakers and participants for making this event a resounding success. Yeah, your contributions, insights, and passion for our multiphysics intelligence have been truly inspiring. Before we part ways, I would also like to thank our organized distributors and volunteers for their tireless efforts in making this conference a smooth and enjoyable experience for everyone. I hope that this talk has been a valuable learning experience for all of us and has sparked new ideas, maybe future collaborations and research endeavors. Let's forward and continue to push the boundaries of knowledge and understanding in the field of architecture in multiphysics intelligence. Once again, thank you all for being a part of this today's event. I look forward to seeing you in the near future. Thank you and goodbye.
Thank you, Professor Yao Jiawei.
Professor Huang, Baojie
Thank you
and
so
John.
much.
Thank you very
Thank you so
much.
Yeah.
Have a good
Have a good
evening.
night.
Or have a good day.
Yeah.
Bye-bye.
Good night.
Bye-bye.
Bye.